I feel like one day we'll have to figure out how to connect projectors properly. All right, thank you for having me. I do not come from this field, so I might have a little slightly different language and take. So I'll ask for apology ahead of time if I butcher some terminologies, and hopefully I'll have some new perspective to share because, you know, adjacent fields with a lot of overlap usually brings in some new perspective. So what I'm going to talk about today is what I call embodied sensorimotor intelligence. And this is sort of adjacent to the field where you guys might have heard about, like, you know, artificial general intelligence, right? And usually they talk about semantic reasoning. There is a table, there is a chair, they should be on top of each other. But I feel like there is another aspect of intelligence that we need to talk about, and that's what I'm going to focus on today. Right? So we as a field, as a community, try to reason a lot about embodied movements, like the previous talk. Like we really try to understand our gait patterns. We try to figure out how these movements emerge and what are the different details of these movements, right? But there is another way to think about it, right? These movements are essentially a readout of the underlying embodied intelligence that we have. Right? We cannot really probe what this intelligence is, but that gives you a readout. The same way we cannot go visit the black hole, but there is a readout that comes out of the black hole, and that's how we know it exists. Right? So if we take this grand view, grand perspective of what embodied movements really mean, it's a readout of this embodied intelligence. And I want to kind of zoom in on this embodied intelligence part and see if we take that grand perspective on this problem, can we think or come up with like new way of thinking about the problem? Maybe new solutions, not necessarily the same solutions, we'll see. All right, so my argument today is going to be that instead of trying to zoom into motor behavior first and trying to understand it with full level of depth and foundations, can we instead approach the problem from like the completely opposite direction, which is what is our behavioral intelligence? And if we can reproduce and understand some part of that behavioral intelligence, does that also tell us anything about the readout of these intelligence, which is back to this motor behaviors? Okay, so I'm going to ask the question slightly in the reverse. And you might wonder, like, this is an idiotic question or idiotic viewpoint. Why would anyone want to do that? And the reason I would like to think that way is because we have seen major breakthroughs that have happened by looking at the problem in reverse. For example, in the field of vision, for a really, really long time, we were thinking about, you know, there are pixels, there are these pixel features, and then we made lots of progress for 2-3 decades thinking about hog and sift features, etc. Then came the era of scaling where a large internet-based data sets got available, and because of these scalings, instead of just making feature-level decisions like it's a cat, it's a dog, it's a rough, grainy pictures, now we have photorealistic and even hyper-realistic reality-bending ability to generate and understand the field. Right? So by looking at the field in the full complexity, we actually found much greater depth of progress. And this is not restricted just to vision. Even in robotics, we were doing small swarm level intelligent robot, small communication between them, and scaling that up into full complexity. Now we have multi-agent, even complex games like AlphaGo have found great strides of progress. We were doing small text embeddings, now we have ChatGPT. We were trying to understand individual protein structures, what each one of these connections looks like, what the energy potentials between them are, and scaling up led to the full protein structure predictions in AlphaFolds, right? So there is valid evidence coming from different fields that just say that if you look at the problem with full complexity, there are strides that we can make that hopefully will unlock new potential, and maybe with some of the existing problems we also have. So what would it mean to us to do that? Let's just say I'm going to take 2 examples, one for manipulation, another for locomotion. Primarily from the manipulation setting, we'll deal a lot with pick-and-place solutions today, right? But can we think of an agent doing the full complexity of the task? For example, this is one of the Rubik's Cube world record holder. I forgot what the total time is, but somewhere around 3 minutes or 4 minutes that he can solve 3 Rubik's Cube like this, right? This is an incredible feat of dexterity and motor control, which are far beyond what we can understand how to reproduce, right? On the right as well, the locomotion behaviors. Like motor behaviors, individual gait patterns, I think we have made a lot of progress in trying to understand that. A lot of sensing capability, technological advancements that will let you zoom into individual muscle level and explain a lot of behavior. But we are far from actually doing what human movements are capable of. So the question is, can we do that? And if we can do that, will it teach us anything interesting? So I'm going to argue, in order to handle questions like this, the existing definitions of what an artificial intelligence has to be broadened a little bit. Primarily, we think of artificial intelligence as a cognitive decision-making process. And this is where neural network comes in and they make semantic decisions. But the true embodied intelligence consists of 2 facets. The first is the ability to make these conceptual decisions and the ability to execute those decisions into physical movements. And both of these facets put together is what makes an individual smart, right? If you remove one of them, you cannot call an individual smart. For example, a complex body as ours, not able to make cognitive decisions, not smart anymore. In the second way, if I can just only sit and think, I might have the brightest thought, but I cannot execute and manifest the thought into the physical world. Again, the same problem. So how do we go about manifesting both of these facets together? And this is what the grand vision probably for our team is. Maybe some of the works that you might have seen from our team resonate with that. Our North Star is to achieve human-level dexterity and agility in physiological digital twin. Right? And towards that mission, we have created a platform that will enable us, or we think is best positioned to get us there. This platform is called MyoSuite. It's fast and physiologically realistic framework that lets us do musculoskeletal and exoskeletal studies. Specifically, what the system has is it has models, which probably you guys are much more familiar than I am. These are models of musculoskeletal systems that are accelerated both on the CPUs and the GPUs. That means these models can run faster than real time and finally can meet the data requirements that the modern machine learning methods have. The second, it goes beyond just the musculoskeletal dynamics. It has full contact and inertial dynamics embedded in the system. That means now you can embed them in functional tasks, so you can do functional studies on these tasks. And these are very generic systems, so you can model anything you probably want, much beyond the complexity of just simple terrain or complex terrain. You can really take it all the way to full-blown physics simulation. And finally, with these 2 capabilities, the group is focused on understanding and learning a lot about the physiological behavior in the full complexity, where our focus is much more on the generalization ability of the agent rather than the production of individual movements. So we really would like to understand how an embodied individual can generalize its decision-making to as wide variety of settings as possible. And hopefully that grand take will fold us back into also being able to understand the individual specifics of the movement. But the latter is much more of a second-order effect for us. We are much more interested in pushing the boundaries of how you can make decisions in much more general sense. Okay, so when we think of decision-making, the question becomes, how do we generalize? We become specific if we have to do one special thing, but that same locomotion ability that let me walk on the flat ground, I can very well generalize if I go to a hiking situation. So the question is, how do we come up with this generalization ability? So let's just start with the thought process, and I'll love everyone can chime in. There are 2 pictures on the left of the screen. And if the goal is that I want to go to a cocktail party and I want to dress up, the question is, which of these 2 situations would I prefer to begin with? Okay, so people who want to begin with on the left picture, if you can raise your hand. No one, okay. The Who will prefer to start with the middle picture? Right? Majority, okay? I thought there will be a couple of ambitious people, but all right, everyone is like me. Let's just do one more, okay? The same question. I want to prepare a salad. The question is, I want to go to a market with everything raw. Anyone would like to start over there? Food fanatics, yes, yes, yes. Someone who appreciates food, absolutely. People who will be in the middle, a couple of us, a little bit more distributed. So let's just see what I actually made you guys think, right? The reason most of us prefer to start in the middle is it's a much more structured space, right? Things have been presented to you in much better form such that your last step of making those actions happen is much more easier, right? And behind the scenes, there are a lot of individuals that have worked to present that unstructured space in a much more meaningful, structured pattern for you, right? And when we start talking about intelligence, who was this intelligent person when they got dressed up? I got the credit. But none of those individuals who actually took my messy room and organized my cupboard got the credit. And that is the missed opportunity, right? The smartness is not in the last step. The smartness is in organizing the space and making it presentable so that the last decision is the easiest one, right? And we're going to try to figure out how we can emulate the first step while most people look at the last. All right? What happened here? In the raw space, there is a paradox of choices. There are too many things to choose from, so our brain gets confused. You cannot do this. It's too hard. All right? And this is an overwhelming sense that we're going to try to avoid. And if we can avoid it, our decision making is going to be much, much easier. So here is an alternate way of thinking about the world. We all know brain makes decisions, so don't take my word literally. But for a second, ask, what does brain do? Is it really in the business of making decisions? And my argument will be today that maybe think about, brain is in the business of building and updating representations. Instead of letting you think about each one of these firing patterns, it lets your consciousness raise above a level so I can just think about much higher levels of abstractions. And as I go through a space, it updates my representation of the space, the new tasks that I'm trying to learn about in such a way that these higher level of abstractions is actually going to help me make that last one-step decision, right? So we all agree it helps with the decision making, but under the hood, I think majority of what the brain does for us, for our motor control, is to help us build and update these representations. Okay, with that viewpoint, let me actually share a few results of what happens if we can think of the brain's responsibility as that. The implications basically is making decisions is much, much easier. Representations can be acquired ahead of time, not exactly when you're actually executing the task. So that's why we went to school, we did a lot of things, that's why I got here. It's not that my brain is processing everything from scratch. Right? And this is where I would say parenting is a hard process, right? You invest a lot in a kid to help the kid build its representation, and then the kid does something, right? Initially, there is a lot of investment, and that's the same process we'll have to go through over here, is when you're trying to prepare these large representations for generalization, the initial hit is going to be large, right? So that brings me to the first result I'm going to share. This result we called MyoDM, which stands for myo is for muscle, DM is for dexterous manipulation. And our goal is for all the 57 tasks that are described semantically in this picture, we want to recover a single agent that can solve all of these tasks. Okay, so can we identify basic constructs of dexterous manipulation that can solve a large variety of tasks, for example, a sample set here, and maybe generalizes to much more beyond that. Let's see what happens if you try to solve the task one at a time. These are very high dimensional tasks, and even if you can solve it, it leads to very degenerate solution. So this is just to say this is a very hard problem to begin with. And anyone who has done optimization in high dimensional spaces, especially musculoskeletal systems, probably can appreciate that, yeah, this happens and I've seen worse version of this. So the question is, can we do better than that? So let me first go through results, and if the internet cooperates, we'll see something. Ah, there we go. Okay, so all the results on this slide and the following slides are coming from a single agent. So for example, you can see this agent is picking up a glass of wine and swirling the glass of wine. Feel that in the motions, the weight of the fluid moving around is also exhibited properly, right? That is to the level of detail of the movements that is being captured. Let's go to the next one. Here, it's a stamping behavior. Feel the pressure that the force that is applying. You can almost see the nuance of those forces also getting exhibited when that pressure is applied in the stamping behavior. Here is a much more dexterous behavior where you're trying to show the flashlight around, and you really have to articulate different joints and coordinate them properly to do that. Some of the cyclic movements are much harder to manifest, so this is cyclic motions, another cyclic motion, and maybe just for the fun of it, none of the results are complete without the Stanford bunny, so here's a Stanford bunny, why not? Right? So the question is, how did we do that? Right? And this involves thinking about approach that involves a couple of key observations. First, instead of trying to solve for that motion initially, do not focus on the motion. Right? Focus on casting the problem in such a way that it is task agnostic, that one instantiation in this giant space is your task, but you have to solve the problem for the entire task. So we're going to build a task agnostic formulation of the problem. Then we are going to build giant behavioral priors. This is the first step of stressing up. And based on those things, the last thing is going to be like the one-step smartness solution. So what is a task-agnostic formulation? From the locomotion community, you can think about this. Like you anticipate your movements ahead of time. You do not talk about, oh, take one step to the staircase one step to the staircase two. There is this general parameterization that you want to follow certain directions and velocities. And as long as you can do that, the underlying terrain can change any way you want, and you want to adjust and adapt to that. So it's a generic formulation. We'll try to do that for manipulation setting. The second is we're going to build a universal behavioral prior for dexterous manipulation. I'm going to talk a little bit about how we do that, and when we do that and combine them, then we can solve all these problems using a single embodiment, a single embodied agent. Okay, so the key takeaways over here are these: we act in our anticipation, and the underlying sensorimotor delays are handled because we act in anticipation. And the generic formulation of the problem is going to help us get around that. And by using this generic formulation, we aid in the composition of the task into specification of the task and generalization coming from specification, and then solving for the task once the specification is done. So all in all, if you zone out on the details, I want you to take away this one key point, that instead of building a task-specific solution, we are trying to build an agent-specific solution. We are training an agent to be able to solve a task. We are not trying to solve a task. Okay? So if you think of it that way, then any new task you throw at the agent, hopefully the agent should be able to handle it. And that's the bigger goal. All right? So the first thing we're going to look into, what are these big priors? Right? So first big prior we all know about, nothing new over here, is object affordances. We all have a mental model of how we interact with an object way ahead of this object given to you. I'm pretty sure none of us have ever seen this glass jar in reality, but just showing at the pictures, you kind of know how we are going to approach and grasp this object. And this, from the vision community, has already been distilled down into a model where it's like, given an object, this prior already exists. You can take it for granted. We downloaded one of these papers, and then we just take it for granted that this paper does the work for us, okay? So there is an object affordance model that we are gonna build in. So this is a prior that is coming in. The second is, what will happen if we take this prior from the vision literature and apply into our domains? So here is just like you can think of it as much more inverse kinematic space mapping of that mano hand into the myo hand, which is what our version of the hand is. And you can see the kind of pre-grasp predictions that this model gives you. So it's already quite reasonable. You can see the pre-grasp like being very, very reasonable. So the overall problem statement looks like that the flexible way of defining the problem is going to be that we are going to track a desired object behavior. There is no constraint on what the object is going to be and what the behavior object can do. But I'm not specifying any way how the agent will act to manifest that. And that's the problem we're going to try to solve. To aid solution of this problem, we are going to bring that pre-grasp prior that I talked about, right? So given any object, you can query the previous model, you can get the pre-grasp prior. And using these two techniques, we are basically going to ask our solvers to solve, right? So the two things I'm bringing in new, apart from all the standard things, is a flexible way of defining the problem, and then a generic prior to help with the solution. Right? With those two techniques, what we see is a general algorithm such as a PPO is able to make strides of progress. So for example, if you see the simple PPO with no pre-grasp priors is much less effective, right? It's 37, it only solves 37% of the tasks we ask for. But just the incorporation of these prior pre-grasp into our system now lets us solve 56% of the task, right? So the heavy lifting, which is coming offline for almost free, is giving you quite a bit of progress. The important details are that there is no task-specific hyperparameter optimization we have done. This is a single model that you can throw any object and any desired behavior you want from that object, and it is able to handle those complexities, right? So now, still not good enough, right? Like we just got 56%. But the problem here is that we, again, in this particular result I'm showing you, solve for one behavior for one object, right? So the generalization didn't kick in. Like we as a humans evolved through our lifespan, and the way we do it is by throwing more and more complex solutions to us. And this is also has been clinically proven that the representations also evolve over time, right? Like as you get more and more capable of your locomotion abilities, the representation space in spinal cord circuits also evolves over time. So the question is, can we do something similar? So there is one way of thinking about it. How about we do teacher-student distillation? For those who know teacher-student, for those who don't, I'm gonna do a very quick summary. It's almost like you train for each one of these individual tasks and you became expert for each one of them. And then you say that like, okay, combine everything at the end of it once you're an expert, right? So it's almost like I studied something for 2 years, didn't do anything else. Then I studied again something for 2 years, didn't do anything else. And at the end, I'm expecting to be the expert of that. That's a student-teacher distillation. But instead, what we say is like humans are multitaskers by default. We train for a lot of things together, and I think being on the far right end of things is the right way to do it, and this is how we achieve our myodex prior. So the way we do it is we throw a bunch of like lots and lots of tasks and ask for task solution from the same agent. And the same agent is learning to solve multiple tasks simultaneously. And whatever is the policy that comes to the end, that is going to be our universal manipulation policy, that is going to be a universal behavioral prior. And if you do that, then all of a sudden, as you can see, the myodex prior can almost solve all the problem, but using a single agent, right? So this is the prior, the building the prior part is the interesting part that is helping us do the most of the heavy lifting, right? I'm gonna just quickly show, in addition to being able to solve most of the tasks, the learning speed is also with stark contrast of how sharply can you learn, right? That's also interesting. You can solve 3 times more tasks than any of the experts that are individually trying to solve the task as well. And then coming back to maybe some of the materialistic thing. Sure, we went full-blown on the other side of the things, try to create, generic agents. But what did we learn about some of the problems in hand today, right? Did anything interesting happen? Maybe this graph tells us like maybe there is some way to fold it back into what we care about. During the evolution process, we also saw snippets of synergies evolved over time. We didn't encode synergies should have existed in order to find these solutions, but that is very interesting. But what is not yet clear is how well these synergies match with the real individuals. We don't know yet. That's a gap that exists, but that is what happens when you take a leap of faith, right? But it's interesting that like these solutions are also finding synergy spaces, which is very well known that our brain employs to reduce the computational burden, right? Anyways, how much time do I have? 2 more minutes? Okay, so I'm gonna skip on a bunch of things and show you guys something cool for the end part, okay? So what are we talking about now, okay? So I gave you a snippet of like, what happens if you look at and try to attack the far extreme of the problem, but then folding it back to some of the materialistic problems we have, that is the challenge, right? And I don't think I answered this question, and you should hate me for that. Right? I distracted you way too much, but I didn't really answer the question that we at the field should be solving today. But let me give you a few takes of what I think could happen and what we are doing in that space, right? So we are building a full-blown model. This is what we call myoskeleton. It's going to be released in some time. In addition, we are releasing a data set of myomotions. Hopefully, internet cooperates. So these are myomotions. These are full body behaviors that are available for you to study. You build your controllers on top. And myomotion is a full-blown API that is designed for really, really large data sets. You can think of petabytes of data. So we are releasing that API because we all have data, right? It's the same way the ImageNet moment came into being is when the entire data set came together for all of us to learn from. And our hope is that you'll join me in making this data set more and more diverse. After that, we are also working with some partners in clinics. For example, you can see some evidence over here of myomotion API as well as the myoskeleton being applied on clinical settings where we are trying to reconstruct the movements. A few more examples over here. This one is from monocular video instead of multi-camera setup. So this is a monocular video of like sit to stand and stand to sit. It's not perfect yet. So you see some jumps occasionally here and there that happens. And offline, maybe I can show you a couple of more weird corner cases where it doesn't really do the right thing, but hopefully we are on the right track. And if you are working in these directions, we'll love to hear and listen from you. Finally, these are like square test, stepping test. I think that's what it's called, right? A square box walking test. I might be wrong on this one, but like I think some of these are real patient data sets coming from those tests, again on the myomotion. And finally, please join me in thanking all those people who have helped me and help all of us to make progress in this direction.
Just one quick question, please. Thank you.
Thank you, Vikash. So I want to ask you a question about the first 75% of your talk. You've got this very robotics flavored approach, right? You have a full state information, I presume, lots of iteration in simulation, no neural constraints, no constraints on the, say, motor learning that can happen. And the results are impressive. You can, it's very nice to be able to manipulate all these objects. My question is, if we're doing big, deep questions today, does this have anything to do with humans? And if so, how do you know?
Yeah, I think this is an excellent question. So does it have anything to do with human if you put this in a spectrum, right? It really depends on which part of the spectrum you are. The fact that I can converse with you today has something to do with us being humans, right? And the ability to fully understand our physiology is the other extreme of it. Even physiology, what it means, like different people will have different definitions. If you ask graphics people, just being able to have like a stick skeleton model is physiology enough. They call like, geometric constraints being satisfied as reasonable enough. When you talk to like people with physics simulation, maybe ground reaction forces is good enough. When we talk to really neuroscientists and biomechanics, the spinal arcs needs to be valid enough. So I think there is a sliding spectrum. Maybe for me, the physical realism, where the reaction forces, etc., are right, is where my line might be closer.
Do you have any plans to compare the output of your model to what real people do in response to similar circumstances?
Yeah, we definitely, that's the whole point of like coming and talking to you guys, and maybe I showed some evidence. We are working with people to actually try to validate some of these things in real settings.
All right, thanks.
Okay, so let's thank you again, Vikash, for his talk. So our next speaker is Serena Ivaldi.